little more time on these? Got it? We take like 2 more minutes, and then we'll go through. All right, let's take a look at these. So 2 similar problems. All problems of this type are basically asking for the same thing. As we talked about last week, they're all pretty much just saying, do we have the right molar ratio? What's the molar ratio needed to complete this reaction? The differences then is in the first problem, we'll call the higher one the first problem, the quantities are given in molarity and grams. And you're given the quantity of one reactant, you have to find the amount of the other reactant. So you have to find the mole of the other reactant, and then we can get the volume. In the second one, we probably have some kind of limiting reactant situation, because we're given the mass of both reactants. So we're going to have to check, based on both reactants, how much product can be formed, and then whichever one forms the least product, that's going to be our theoretical yield of aluminum oxide. All right, so let's do them one by one. I'm going to move this out of the way. Let's see if I can do that. No, I guess not. Let's just get that one out of the way for now. We'll add a couple more pages here. All right, good enough. Okay, so to look at this one, we're given the mass of sodium bicarbonate, and we need to find moles so we can get moles of HCl. Pretty much all these types of problems can be done, in one line. If it makes more sense to you to do it kind of in separate steps, that's fine too. So we're going to start here with our 23.2 grams of sodium bicarbonate. And so we want to go from grams to moles of sodium bicarbonate. And then get moles of HCl. And then instead of getting grams of HCl, since we're asked for how many milliliters of a particular molar solution, we're going to try to get volume. So we're going to go from moles of HCl to liters of HCl, and then finally we can get milliliters in our usual way. All right, so once we work out all the units and we make sure everything's canceling properly, then we can add in the actual amounts. So the moles per gram for sodium bicarbonate, that's going to be the molar mass, which is given. Whoops, I just did that backwards. Because that's grams per mole. So 84.02 grams per mole. Then based on the coefficients in the balanced equation, it's 1-to-1 between HCl and NaHCO3. To get from moles to liters, that's where we use the concentration. So we recognize that the HCl is 1.58 molar, so 1.58 moles per liter. All right, and then we should be able to calculate that. Maybe. So 23.2 divided by 84.02 divided by 1.58 times 1,000 is about 175 milliliters. So it's probably D. Is that what you got? All right, great. Okay, let's move on to the next one. So this one, we're only dealing with masses, we're not dealing with solutions, but it's probably a limiting reactant situation because we're given the quantities of both reactants. So we need to solve for the theoretical yield based on each. Now, another thing that you could potentially do here, and some questions make it easier than others. This one's probably a little too, the numbers are a little too weird to do this. But you can also sometimes look at the ratio of the reactants and just sort of like figure out what the limiting reactant is and save yourself a step. Like we know there's a 4-to-3 ratio in moles between aluminum and oxygen. Oxygen O2 is going to be a little bit heavier than aluminum. So the fact that we have more oxygen doesn't necessarily make it obvious which one's limiting in this case, but sometimes like if it were the opposite of that, like if we had way less oxygen and it was heavier, we'd know we'd have fewer moles of oxygen and therefore it would have to be limiting. So sometimes you can just kind of tell by looking at it if the numbers work out. This one is a little too close probably for that, so we should just calculate it. So we're going to do that same calculation, just do it twice based on each one. So 82.49 grams of aluminum. And we're going to go from grams of aluminum to moles of aluminum. And then moles of aluminum to moles of oxygen. And then moles of, not moles of oxygen, moles of aluminum oxide. And then moles of aluminum oxide to grams of aluminum oxide. Okay, then we just need to fill in our numbers and calculate it out. So our aluminum mass is 26.98 grams per mole. The equation tells us that we have 2 moles of aluminum oxide for 4 moles of aluminum. And then our aluminum oxide is like that. We'll set up the other equation too, and then we'll calculate them both together. So the other one is starting with 117.65 grams of oxygen. And we're going to convert to moles. Do our molar ratio to get moles of product. And then solve for the mass of product. In this case, it's 3O2 for 2 Al2O3. And then again, the same mass, 101.96 per mole. All right, so for based on aluminum, 82.49 divided by 26.98 times 2 divided by 4 times 101.96. Looks like it's going to predict about 155.9 grams of aluminum oxide. The other one, if we start with 117.65 grams of oxygen divided by 32 times, whoops, not squared, let's try that again. 117.65 divided by 32 times 2 divided by 3 times 101.96. 249.9. So what's the actual theoretical yield? Yeah, the lower one, 155.9. That's how much we would plan to make, which tells us what's the limiting reactant? Aluminum is limiting and oxygen is in excess. All right, remember with these types of questions, the question itself doesn't have to say anything about limiting reactant. It doesn't have to say find the limiting reactant or first find the limiting reactant, then find the theoretical yield. It just gives you some amounts. It's up to you to figure out, we're given two amounts of each reactant. We got to figure out which one's limiting and calculate from there. Okay, questions about doing those sorts of calculations? All right, as you can see, they're all pretty similar. So if you practice this and kind of do it over and over again with slightly different wording questions, going through the homework, going through the chapter, there's really nothing new that you can see about these things. So you should be well prepared for a quiz or an exam. All right. So the next thing we're going to do, we talked about pretty much everything in Chapter 4. I left out a couple slightly different topics, so we're going to take a look at those now. One is oxidation-reduction reactions, and the other is titrations. So let's look at oxidation-reduction first. So does anybody know, has anybody heard these terms before? Do you know what oxidation-reduction refers to? What that's talking about? That's a good thought. I think you're thinking of equilibrium. Equilibrium reactions go back and forth. There's something that happens in oxidation-reduction reactions that has not happened in the other types of aqueous reactions that we've seen so far. Any idea what it is? Any guesses? Nothing? Too early for guesses? Brain's not working yet. It's electrons. In oxidation-reduction reactions, these reactions always involve the transfer of electrons between reactants. So rather than ions just like switching places and forming precipitates or forming a gas or making water in an acid-base reaction, you're actually changing the electrons on the different atoms. So some electrons from one reactant are going to a different reactant. And the most obvious way of identifying these reactions is when we see ions or atoms changing their charge. So like a classic oxidation-reduction reaction that you've probably seen written before somewhere is if you take solid sodium and you react it with chlorine gas. We're not going to do this. It's super dangerous. You form sodium chloride. That's an example of an oxidation reduction, aka redox reaction, because the electrons have transferred. So on the left, we have neutral atoms, right? Sodium by itself as a metal is neutral, has no charge. Chlorine by itself as an element, also neutral, no charge. But sodium chloride, we know, is an ionic compound where sodium is +1 and chloride is -1. So in order for that to happen, electrons needed to transfer from the sodium to the chlorine. So if we think about the electron counts on sodium here, if we go kind of back to chapter 2 for a second, and we're looking this up, sodium's going to have 11 protons and 11 electrons. And sodium ion has 11 protons and 10 electrons, right? We did those kinds of counts a long time ago. So that electron had to go somewhere, and the place it went is to chlorine. So it turns chlorine, which is neutral, into chloride. And that makes it an oxidation-reduction reaction. Those definitions are oxidation is the loss of electrons, and reduction refers to the gain of electrons. So whatever is losing electrons is oxidized, and whatever is gaining electrons is reduced. So we would say, in this case, sodium is being oxidized, is losing its electrons, and chlorine is being reduced, it's gaining electrons. See how that works? Okay. If we go back to look at something like our aqueous reactions from before, let's just jump back to the old days here. We'll grab that one. So if you take a look at that reaction up at the top there, we've got potassium chloride, lead 2 nitrate, typical aqueous reaction, precipitation reaction. Nothing changes charge in that entire reaction. Potassium is +1 the whole time, chloride is -1 the whole time, lead is +2 the whole time, nitrate is -1 the whole time. Everything's keeping its charge. So that's why these types of reactions are not oxidation-reduction or redox reactions, because nothing changes its charge. Nothing changes, no ions change their charge. Now the thing that can get a little bit tricky about recognizing these reactions is that non-ionic compounds also do redox reactions. So covalent compounds, molecular compounds also do redox reactions, which means they transfer their electrons, but they're not charged. They're not ions. So we need a way of figuring out where the electrons are going, where they're coming from and where they're going, even with things that are not charged. And for that, we use something called oxidation states. Oxidation states are the way that we keep track of electrons. They're not exactly real in the sense that you can see them, you can see the effects of them, but this way we can talk about things like kind of similar to charges, but with compounds that are not charged, so with covalent compounds. So what we do is we follow a set of rules, and using the set of rules, we can assign an oxidation state to any atom in any compound. And these will kind of look like charges because oxidation states are also given as +1, +2, +3, -1, -2, -3, and so on. They can be much bigger than charges. You can have +6 oxidation states and things like that. They're not really charges, but they kind of look like charges. And so we're going to learn how to assign them and practice them here. All right. So assigning oxidation states You have to follow these rules in order, which means that earlier rules take precedence over later rules. So the first rule of oxidation state is that the oxidation state in a free element is always 0. So if you have copper, that's just copper, the oxidation state is 0. If you have a molecular compound that is still a free element, like Cl2, the oxidation state of chlorine is still 0. Even if it's much bigger, like sulfur is known to form S8, these rings of sulfur ions. But again, it's just sulfur. There's no other elements there. So we consider that to be just 0. Hopefully, that's an easy one to remember, because that's also a really good clue whenever you're dealing with reactions that involve free elements, that involve pure elements. They are always redox reactions. They're always oxidation-reduction reactions. Because if you start with some kind of element and then it becomes a compound later, it has to change its electron count to do that. So that's a good place to start always. Second, the oxidation state of a monoatomic ion is its charge. This is also fairly straightforward. So if you have a sodium plus ion, the oxidation state is +1. If you have a fluoride ion, the oxidation state is -1. So it's just equal to the charge. All right. So now let's say we don't have a free element, we don't have an ion, a monoatomic ion. We're going to start looking at compounds, polyatomic ions. How do we figure out the oxidation states for those? So first, if you add all the oxidation states together, you have to equal the overall charge on the compound or ion. So if we have something like water, and we're trying to figure out the oxidation states of hydrogen and oxygen, we're going to talk about how to do that in a second. But what this rule tells us is the H oxidation state plus another H oxidation state plus the O oxidation state has to equal 0, because the overall compound is neutral. That means one of those states is going to be positive, one of those states is going to be negative, so that they can sum to 0. If it's a polyatomic ion, like nitrate, the oxidation state for nitrogen plus 3 times the oxygen's oxidation states would have to all sum up to -1, because the overall charge on the ion is negative. So all the individual states have to add up to the overall charge of the molecular ion. What's going on here? What is the computer angry about now? Okay, we're okay now, I guess. All right, number 4. Metals and compounds always have positive oxidation states. We know if they're by themselves, their oxidation state is just 0. But if they're in a compound, it's always going to be positive. So if you're in a compound like NaCl, you know that sodium is going to be positive, and the oxidation state is going to be +1 because it's an ion, and we know that it's going to be +1. Okay, and then if you get through all that stuff and you still don't know the oxidation state of your atoms, which now we're just basically talking about covalent compounds, so things like H2O, CO2, those types of compounds. You don't have any metals, we don't have any free atoms, we don't have any monatomic ions. How are we going to figure out the individual oxidation states? We assign them in this particular order. That basically has to do with how commonly this particular atom can change its oxidation state. So the order goes: fluorine is -1, hydrogen +1, oxygen -2, anything in group 7A, so the halogens -1, anything in group 6A -2, and anything in group 5A -3. Okay. But in that order from top to bottom. So that means that if you have a compound that has hydrogen and oxygen, like water, you assign the hydrogen first before the oxygen, because the oxygen, there's more of a chance that it's not what it is on this table. Let me show you what that means. So now we have all the rules. Let's practice how this actually works. And let's start with 2 compounds, water and hydrogen peroxide. So with water, none of the rules 1 through 4 apply, because we don't have any metals or ions or anything like that, free atoms. So we have to use this table. So we would say, okay, according to this table, we assign the H first and then the O. The H we assign as +1. And then we assign the oxygen based on the third rule, the fact that they have to add to 0. So if we're saying that hydrogen is going to be +1, what does oxygen have to be to make the overall thing neutral? -2, right? So oxygen has to be -2. So now let's try the same thing with hydrogen peroxide. Again, hydrogen is the priority on this table, so we assign hydrogen as +1. So what's the oxidation state of oxygen in this case? It's -1. So that's why the table is set up the way it is. Hydrogen almost never has a oxidation state other than +1 or 0. The exception is there's a hydride ion that can be -1. But oxygen can be sometimes not -2. And so that's why we assign hydrogen first. All right, so let's practice this with some other types of compounds, and then we can look at how to actually find redox reactions and figure out what's going on in that reaction. So assign oxidation states to each element in the following compounds. Okay, so here's four compounds. 2 of them are kind of related to each other. Assign the oxidation states of all the elements in those 4 compounds. These are all like that, follow that rule 5, basically. Rule 5 and rule 3. If you want to write these down, I'll go back up to the rules so you can see that. So you don't need the first 2 rules for this one, but you do need these. All right, did you get some numbers? You just follow the table, right? So, and then kind of do the math. So in this case, which one do we assign first, carbon or oxygen in CO2? Oxygen, right? Look at the list. It goes fluorine, hydrogen, oxygen. In fact, carbon's not even on the list. So we got to assign those first. So oxygen's oxidation state is assigned first as -2. And then carbon's oxidation state has to be +4. Okay. Now remember, this is not an ionic compound. We are not saying that carbon is a ion, is a +4 ion. This is just a way of accounting for the electrons and saying basically that in this compound, the electrons are hanging around the oxygens more than the carbons. For this, what we're using this for is to identify oxidation-reduction reactions, figure out what's being oxidized and reduced. If you do future chemistry classes, this becomes way, way more important. And you can determine a whole lot of stuff about reactivity and what's actually going to happen in a reaction based on oxidation states. Different oxidation states of elements behave in very different ways chemically. All right, next one, CH4. What do we assign first? The hydrogen, yeah. So the hydrogen oxidation state is going to be +1, and that means the carbon oxidation state is what? Yeah, it's got to be -4. So let's take a look at those and kind of what that means. So you can see carbon, the reason it's not on that list of assignments is that carbon is highly variable in its oxidation state. It can have a lot of different ones from very positive to very negative. And so you can think about that in terms of like what you know about those compounds. The first one is carbon dioxide. The second one is methane. Methane is like natural gas, the fuel. So in methane, carbon is in a highly reduced state. So when it can react with oxygen, that's where that word oxidation comes from in the first place. When it reacts with oxygen is when it burns, forms carbon dioxide. So then it's very oxidized. So in that reaction, what's really happening in a combustion reaction is that carbon is giving a lot of its electrons to oxygen and becoming more oxidized. Carbon is, in this case then, for that particular example, carbon is much less reactive in a higher oxidation state. Other elements can be the opposite of that. All right, for these then, the only thing we have to be careful of is the charge. So the overall charge of -2 means we don't want the oxidation states to add up to 0. We want them to add to -2. So we'd assign oxygen first based on the table as -2. And then our sulfur oxidation state has to be what? +6, yeah. Because we want it overall to add to -2. So if we have 4 oxygens and they're each -2, that's -8. And then we need a +6 sulfur to get to -2 overall. Same idea over here. Oxygen is going to be -2. Sulfur in this case is +4. And that is a consistent difference that you'll see in those polyatomic ions. The ones with the 8 prefix are the ones where the atom is most oxidized. This is the highest oxidation state. And then when they get, actually the per whatever 8, if that exists, is the higher oxidation state. And then as you get to the ite and the hypo, like hypochlorite, that's when they're in lower oxidation states. All right, so you think you can do this? You assign some oxidation states? Okay, so one way that we're going to use things like this, we're going to look at a reaction, and you need to decide first, is it a redox reaction? Is something oxidized and reduced? And then second, what's oxidized and what's reduced? All right, so here's your reactions. I'm going to find it here. I'm going to give you 2 reactions. If it's a redox reaction, what's oxidized, what's reduced? If it's not, then just say it's not. Oops, not equals. All right, so before we assign any oxidation states, can you tell right away for that first one whether or not it's a redox reaction? It is. How do you know? Yeah, so you've got 3 elements on the left and you've got compound on the right. If you've got 3 elements that end up being in a compound, there has to be some exchange of electrons. So this one we know has to be redox. So now assign the oxidation state and decide what's oxidized and what's reduced. Oops, I made an equal sign again instead of an arrow. All right, you figured it out? So we know that at the beginning, the oxidation state of barium has to be 0 and chlorine has to be 0. What's the oxidation state of barium at the end? +2. And what about chlorine? -1. Yeah, each. So each -1, so -2 overall. So barium in this equation goes from 0 to +2. Chlorine in this equation goes from 0 to -1. Which one is an example of oxidation? The barium, because it's losing electrons. It's becoming more positive. So that's oxidation. And that means the other one is reduction. They always have to go together. Electrons can't just magically disappear or appear. So as long as you can figure out one of them, the other one's always got to be the opposite. Okay, what about the second one? What do you think? Is this one obviously redox or not? It's really not obvious. So we have to actually figure out the oxidation states of the elements on each side and then determine what's going on. So go ahead and try that. So what'd you find? Still working on it?
No.
You got it?
So for the hydrogen, it's going to be +1, which is oxidation. And for the sulfate, it's going to be reduction with -2.
Well, hold on. Well, let's take a look at this. So in this compound, we've got two atoms, sulfur and oxygen. Based on the table, we assign oxygen first. So oxygen's -2, and that means sulfur has to be +6, right? So then in the next one, water, we just did that one. H gets assigned first as +1, and O gets assigned second as -2 to make a neutral compound. So then if we look over at the sulfuric acid on the other side, we've got now 3 elements in the compound. Let's write them down in the order that they need to be assigned. So hydrogen's going to get assigned first, then oxygen, and then sulfur based on the table. All right? So hydrogen gets assigned first as +1. Oxygen gets assigned second as -2. So what does sulfur have to be then to make an overall neutral compound? +6. So what does that tell you about this reaction? It's not a redox reaction, that's right. Why not? Because, well, no, it's not that. It's the change. Look at the change from left to right. Is there any change in oxidation states? There's no change in oxidation state. So that means that no electrons have been transferred from one element or from one compound to the other. So that's not redox. There's no oxidation. There's no reduction. There's no transfer of electrons here. All right, see how that works? So sometimes it's really clear and obvious. Other times you have to actually go through and look at all the individual oxidation states and then figure out is there a change or not. I want to give you 2 more definitions that are associated with this before we move on. They're a little bit confusing, but a lot of times, especially in like the safety literature and depending on what context we're in, we use other terms to describe oxidation reduction, and those terms are oxidizing agent, or sometimes oxidizer, and reducing agent. So for instance, in the safety pictograms, there is one specifically, it's a fire over an O, which specifically is saying oxidizer, which means something that is usually reactive because it can oxidize other stuff. The reason this is confusing is the oxidizing agent is actually the thing that gets reduced. It's the thing that takes electrons from the other thing. So the reducing agent is the one that gets oxidized, the one that loses its electrons. So the oxidizing agent gains electrons, the reducing agent loses electrons. That can be confusing because we said oxidation is the loss of electrons. That's still true, we're not contradicting ourselves, but the agent is the thing that's doing it, so it's the other one. One way to kind of keep this straight or to remember it is the absolute classic oxidizing agent, the one that everything is named after, is oxygen. Oxygen is a good oxidizer. So what does that mean? That means oxygen takes electrons off of stuff. Oxygen takes electrons off of stuff. And the way that we can remember that is that we know that oxygen likes to get reduced to oxygen 2-. So it takes electrons to become 2-. Oxygen never becomes positive, at least in the situations that we're going to see in regular chemical situations. So oxygen's always that oxidizer. So if you get a little confused with that, with those definitions, that can be helpful. Is it just a test or something? Okay, didn't sound like a fire alarm really. But, all right, so that's oxidation reduction. Just like anything else, take some practice. Make sure that you can assign these numbers to your compounds. All right, and the last thing that we are going to look at in this chapter that is actually not really anything new, but it does have its own separate section in the chapter, so we will look at it. We're going to do this more in lab. I think next week we start titrations in lab. But the way a titration works is you have, how many people have done titrations before? You don't know? Okay, so not very many. The way a titration works is you have an unknown concentration of some solution. And then you add a known amount of a known concentration solution until it's all reacted. And you add just enough to get to exactly that point where the molar ratio is exactly right. The stoichiometric ratio is exactly right. And then from that, you can calculate how much of the unknown there was, because you know you can do the chemical equation and figure that out. This is most often used for us, or in this class with acids and bases, because it's easy to find that exact endpoint, because that's when everything becomes neutral. So we'll mostly be talking about acid-base titrations, but there's lots of other types of titrations too. Anything that you can define, that you can easily find that endpoint where there's an exact molar ratio, you can do this with. And if you go on and take more chemistry, you'll do lots of other different types of titrations. We're just going to do acid-base titrations here. And so you're going to answer questions like this. And what I want to kind of impress upon you with this is not anything new. This is standard stoichiometry stuff, just in the context of acids and bases. So here's what a typical titration question might look like. Oops. So 20 milliliters of unknown concentration sulfuric acid is titrated with 22.87 milliliters of 0.158 molar KOH. To the equivalence point. What is the concentration of the sulfuric acid? All right. So the language here is something that's new that you maybe haven't heard before. Titrated with, equivalence point. But the calculation is not anything new. What this is saying is when there is an exact molar ratio as dictated by the equation of KOH and H2SO4, you've used 22.87 milliliters of 0.158 molar KOH and an unknown concentration, but 20 milliliters of that for the sulfuric acid. So we start by setting up an equation, just like any other solution-based stoichiometry problem. We need the equation, and then we're going to figure out the moles. So our equation here is H2SO4, sulfuric acid, reacts with KOH in an acid-base reaction. We know the products of that acid-base reaction are going to be water and potassium sulfate. Right? We can, we need to balance the equation. I think that does it. Okay. And now we can figure out our moles just as before. So just to remind ourselves, I'm going to write it right here. So we have 20.0 milliliters, and we don't know the molarity. That's what we're trying to figure out. For the KOH, we have 22.87 milliliters, and we do know the molarity. So that means that since we have a volume and a concentration, we can figure out the moles of KOH. We can use the molar ratio from the equation to figure out the moles of H2SO4, and then we should be able to figure out the molarity of H2SO4 from there. So let's do that. So I'm going to convert from milliliters to liters, and then multiply by the concentration. So that gives us the moles of KOH, 0.00361. Okay. We use the molar ratio to figure out the moles of H2SO4. In this equation, it's 2 to 1, so 1 mole of H2SO4 per 2 moles of KOH. We just get that from the equation. So let's see, I guess we'll have to round that. Okay, and then to get that final concentration, it's just moles per liter. So 0.00181 moles of sulfuric acid divided by the liters of solution, which is 0.200, Oh, too many zeros. So that tells us that our sulfuric acid is 0.0905 molar. Titration is kind of like a classic chemistry class lab thing, but it's also actually a useful professional technique. Titration is used all over the world when we need to know concentrations of various liquids. Especially because you can't always, so when we talk about molarity, you talk about dissolving a solid in a liquid and then like measuring that. But you can't always actually do that accurately. Sodium hydroxide is a good example of that. Sodium hydroxide absorbs water from the atmosphere. So when you're measuring out a mass of sodium hydroxide, that's actually not a very precise mass of sodium hydroxide. So if you actually need a precise amount of sodium hydroxide, what you have to do is dissolve it in the liquid about what you think you need. And then you need to standardize it with a solution that you do know the concentration of very, very precisely. There are other solids that you can dissolve in water very, very precisely that don't absorb other things like that. So titration can be used for something like that. It can be used for finding unknown things. Lots and lots of different reasons that we use titrations. All right, I think there's a couple problems like that in the homework. And you'll see those more in the future as we do those labs. Okay, so with our last 5 minutes, for lab tomorrow, we have the limiting reactant lab. Let's just take a quick look at it. This lab is, it's a good lab. It's definitely something that takes some thought in terms of like figuring out what you're supposed to do. I'm going to frustrate you a little bit on this. I'm not going to tell you the answers. When you get to the frustrating parts, I will certainly, whoops, that's the wrong class. I will certainly help you the best I can, but you have to figure this thing out. So let me show you what that looks like and how you can prepare a little bit for tomorrow morning to make sure that you're successful with that. All right, so you got a few pre-lab questions to answer. Should be pretty quick. Just kind of some definitions, make sure you know the equation, all the formulas, that kind of thing. Shouldn't take you too long. I would like you to also please read through this procedure carefully. This is one where you may not need to do a lot of notebook prep for this. Just the standard, like get your title and stuff ready, because you're going to be working through this procedure and writing your observations as you work through it. So just keeping everything clear and neat is fine. But this is definitely a lab where you don't want to be going in the morning having not looked through this and trying to follow it as you're doing everything else with all the chemicals around. It's not a super straightforward procedure. It does take a little bit more than what we've done in the past. So please read through this and get kind of a picture in your head of what it is that you're going to be doing. What are the steps that you're going to be taking? What are the things that you need to watch as you do that before you come in? This is not quite a simple enough lab that you can just sort of show up and do it. So look up terms that you don't know or parts of the apparatus that don't make sense to you. And I'm not going to require you to write anything other than the regular pre-lab questions, but the more prepared you are, the better it'll go tomorrow, the quicker it'll go tomorrow, and hopefully the better results that you'll get. Other questions? Oh, and I will have your exams for you in lab tomorrow, so we can look through those too while you're waiting. There's some waiting in this lab, so that'll be something you can do while you're waiting.